In the crude tower, the distillation unit is comprised of the pre-flash tower, atmospheric tower, and vacuum tower, regions that are all susceptible to corrosive species. When amine scavengers used to treat hydrogen sulfide is used, tramp amines may form. These tramp amines can react with hydrogen chloride and form corrosive salts that can deposit in the CDU and cause underdeposit corrosion in the CDU and various parts of the crude tower. Underdeposit corrosion from corrosive amine salts have rates about 10 to 100 times faster than naphthenic acid corrosion. Refiners have shared experiences of corrosion in the crude tower. At an American Fuel and Petrochemical Manufacturers Conference, a panel member from HollyFrontier said atmospheric tower corrosion mostly comes from inorganic acids such as hydrochloric acid, while the vacuum tower overhead typically suffers from low pH corrosion when processing high-tan crudes. An attendee from CH2M Hill mentioned that while pre-flash drums pose an insignificant corrosion problem, for pre-flash towers with separate overhead systems from CDU towers, corrosion is more of a concern because water partial pressure in the atmospheric tower overhead will greatly increase, resulting in severe liquid phase chloride corrosion. At the 2013 American Institute of Chemical Engineers, a speaker from Petrobras suggested to reduce chloride content in vacuum diesel. The fractionation reflux rate in the vacuum pump rounds should be raised. A U.S. refinery in South Texas experienced more corrosion after processing an increased amount of light tight oil from the Eagle Ford Formation. This practice led to an increased formation of tramp amines, leading to salt corrosion in overhead bundles. If multiple bundles were to fail, this would result in an unplanned CDU shutdown, possibly costing the refinery more than $4 million a day. According to the refinery, corrosion issues can be minimized by adding caustic and increasing the minimum hot drum temperature. A refinery in the Gulf Coast once experienced 3 CDU shutdowns over 2 years caused by corrosion in the pump-around exchanger overhead. While an analysis of the deposits found amines from the neutralizer and the plant amine from the refinery acid gas removal unit, surprisingly, amines from MEA scavengers used to treat hydrogen sulfide upstream were found. This led to increased salt corrosion. Even though the refiner had good chloride control and desalter performance, amines from MEA scavengers still caused salt formation and subsequent corrosion in the tower top pump around section. A company developed a technique to create salt formation curves to understand and prevent corrosion due to salt formation in the overhead of the crude unit. The company analyzes output data from its ionic equilibrium model at various operating conditions to develop these salt formation curves. Ongoing amine mapping and amine speciation is also performed to determine which amine is driving the salt point to determine salting frequency. Once salting frequency has been established, operating conditions are optimized to ensure reliable operation of the CDU overhead. A vendor and a refiner worked to develop a salt point operating envelope to manage salt formation in the atmospheric tower, allowing the refiner to set the tower top operating temperatures in a safe range to prevent corrosion while also increasing distillate production from the tower. Based on the developed salt operating envelope, the refiner was able to see the amount of time salt was being formed in the tower based on operating conditions. Because the point at which the tower transitions from not forming salt to forming salt is a function of both the acid and base, the refiner was recommended to better manage both amine concentrations and chlorides in the overhead. The refiner later developed key performance indicators to optimize operating conditions, allowing simultaneous management of overhead corrosion and increased diesel production from the atmospheric tower based off the results of this salt operating envelope. Refiners and companies have worked together to determine causes of corrosion. In 2009, Irving Oil and Baker Hughes worked together to study multiple corrosion mechanisms occurring at once, mainly hydrogen sulfide corrosion and ammonium chloride corrosion, and corrosion caused by increased flow velocity. The cause behind these problems was determined to be a combination of crude type and operating conditions. In 2016, PermaSense used a combination of sensors and computer modeling to determine the root cause of increased overhead corrosion at a European refinery. Nalco Champion used this data to calculate changes in process operations that contributed to corrosion. Major U.S. oil refiner Chevron and the University of Saskatchewan teamed up to conduct a series of experiments to find a way to better assess crude oil corrosiveness. The idea behind this was to use X-ray technology to quantify and identify sulfur compounds that cause corrosion. The technique, called sulfur K-edge X-ray absorption spectroscopy, uses medium energy or tender X-rays that allow refiners to collect data on sulfur species and add them to a library to better identify corrosive compounds.